Assalamu alaikum. It's our 13th lecture of Advanced Electromagnetic Field and Waves, and in this lecture we are going to solve parallel polarization of electric and magnetic field. To do so here is the illustration. So we have two regions, you can say. This is my first region and this is my second region, and in first region there is an incident wave and the reflected wave also in region 1, and in region 2 you can see there is a transmitted wave, and this x-axis line is basically the normal line. Normal line is always between the incident and the reflected. This is a very conceptual part. You must have to know how that the normal line always make in between the incident and the reflected wave. So this is the incident and this is the reflected, so definitely the in between line is the normal line. Okay, and if this is the normal line, the other axis line is basically the tangential line. So this is basically the tangential line, and let assume that our tangential line axis is z-axis and our normal line axis is the x-axis. Now what we have to do, we have to make the electric field and wave propagation lines. So for that, let us first make the electric field, wave propagation and the magnetic field directions of this incident, reflected and the transmitted wave. Now here you can see in the region 1 there is an incident wave and the reflected wave, and the incident wave for the parallel polarization, the electric field in this direction. Okay, let's assume you can also take electric field in this direction, it's up to you. The only correspondence magnetic field sign changes, don't worry about that. So electric field in this direction and wave propagation in this direction, and to find the direction of the magnetic field h, you know that we have to use the right hand rule. Align your thumbs in the direction of the electric field, and what you have to do that, and align your thumb in the direction of the wave propagation, then definitely the curling of finger denotes that the direction of the magnetic field. We already find the direction of magnetic field in previous videos many times, so you can find easily. Okay, so apply a right hand rule here and apply a right hand rule here, you can conclude that the magnetic field is into the page. Okay, for the case of into, we have to use this small cross sign. So this is hi, means magnetic field. For the case of incident is into the page, and this is hr, means the magnetic field in the reflected part, and this is also in into the page. And for the case of the transmitted part, again the magnetic field is into the page, denotes that the magnetic field is into the page, and magnetic field and electric field and the wave propagation are always perpendicular to each other. Okay, now what you have to do, you have to split your electric field and magnetic field in components. Okay, so in parallel polarization, what is the main thing is that you have to make the components, subdivide your electric field components as well as your wave propagation components. Okay, so in parallel polarization we are going to solve perpendicular polarization also in next lecture number 14. Okay, in that the scenario is somehow different from now. Okay, so here, but in this scenario, like you have to make components for the case of electric field and the wave propagation. To do so, what you have to do, you have to make this normal line and this tangential line on all the center points of these waves. So let me draw that perpendicular coordinates and then have to draw their respective components. Here I just illustrate the perpendicular components. You can see this and this and this and this and this and this. Now you have to drop your components. So how you can drop? So this is the electric field. So always the tangential component drop on the electric field. You know that this is the tangential line. So you have to drop this, okay, like this, okay, and this direction. So this becomes your theta incident. Okay, again, first of all, I have to know how you that the incident angle is this, which is theta I. This is your reflected angle, which is theta r, and this is your transmitted angle, which is theta t. Your angle made always with the normal line, so this is the normal line, so angle made with the normal lines. Okay, again you have to subdivide your components of the wave propagation also, and your wave propagation always drop on the normal line. So this is the normal line, so you can drop like this, and this becomes angle theta I. Understood? So in front of theta there is sine theta, so it becomes sine theta I. Okay, but this is in the negative x direction because x direction is upside, so this is in negative x direction, so it becomes minus x. And this is the base, so it's basically cos theta, and this is in the positive z direction, you can see, so that's why it's become z cos theta. Similarly, in front of theta, this is the vertical component, which is the sine theta, so you can write here as sine theta. Okay, and this is in the z direction, so it becomes z sine theta. Whereas this is the base, so it becomes basically cos theta, and this is in the positive x direction, so it becomes x cos theta. Similarly, you have to write this for the case of reflection. Again, this is your tangential line, so it drops like this and this. So this is becomes theta. Theta in front of theta is basically the sine theta, and this is in the negative x direction, so it becomes minus x sine theta. Okay, and this is basically the base, so it becomes cos theta, and this is in the negative z direction, so it becomes minus z sine theta. Sorry, cos theta. Now again, this is the wave propagation direction. You have to make components with the normal line. So you know this is the normal line. So here it makes like that. So this is becomes angle. So in front of this becomes the sine theta. So this is sine theta, and this is in the z direction. So it becomes z sine theta, and this is the base. Base is basically the cos theta, and the base is in the negative x direction, so it becomes minus x cos theta. Similarly, for the case of this, again you have to, this is the tangential line, electric field drop line like that. So this is theta t becomes it, and in front of theta is basically the vertical component, which is sine theta, and sine theta is in the negative x direction. Similarly, your this is base, it is cos theta, and cos theta is in the positive z direction. Similarly, for the case of the wave propagation, again it drops with the normal line. This is the normal line like that. So this is basically the sine theta component in front of theta t, and this is in the positive z direction, so it becomes z sine theta. Similarly, this is in the base, which is the positive x cos of theta. So this is how you can make the components for the case of parallel polarization. Now the next step is to find the and to write the equations in region 1 and region 2. You already know that this is my region 1 and this is our region 2. In region 1 there is an incident and the reflected wave, and in region 2 there is the transmitted wave. So now let's make the field equations in region 1 and region 2. Now these are the field equations in region 1 and region 2 for the case of electric and magnetic field H. Okay. So in region 1 concern, there is incident wave and the reflected wave. So while writing the equations of either electric field or magnetic field, there is a sum of incident plus reflection. So that's why you can see this first is basically the incident for electric field, and plus this means for the case of incident plus reflected. Similarly, for writing the field equations for magnetic field, This first term is basically for the incident, and this second is basically for the reflected. So sum of both and sum of both. While the region 2 concerned, there is only the transmitted wave, so there is only one term. You can see transmitted electric field and transmitted magnetic field. So how you can write the field equations? As you know that the you can see that the electric field is subdivided into two coordinates, z and x. Similarly, your k wave propagation also splits into two components, x or z. Okay, so whereas electric field concerned, so electric field direction is positive z cos theta I and negative x sin theta. So you can see positive z cos theta I minus x sin theta I. Okay, and whereas e naught I is basically the amplitude in the incident. When we are writing e naught r, it becomes the reflected amplitude. So E equals to E naught I, which is the incident amplitude, and the direction is basically the sum of these two components in which electric field is dividing Z cos theta I minus X sin theta I. Z cos theta I minus X sin theta I. Similarly, now you know that how you can write the field equation for electric field. E equals to E naught, the direction, and E power iota E power iota K1, direction of the wave propagation, k minus iota omega t. This is the basic general equation, but when the components are subdivided, so you can see the direction is subdivided is the sum of the two directions. Okay, when also the wave propagation when divides, so you can see e power iota k1. Why k1? Because you are in the first region. When you are in the second region, it becomes k2, but when you are in first region, so it is k1, and the directions is subdivided. For the case of wave propagation, you can see x cos theta and positive z sin theta. So you can see positive x cos theta and positive z sin theta. Okay, this is this subdivision of the wave propagation direction minus iota omega t as it is. Now the incident is done for the case of electric field. Now you have to write the same procedure for the case of reflected, and for the case of reflected, the amplitude is now e naught r, so it becomes e naught r. Now the you can see this term. So electric field again divided into minus x sin theta and minus z cos theta. So you can see here minus z cos theta minus x sin theta. The direction of electric field is subdivided, while e power iota k1, because you are again in the first region, so that's why again here is k1. And the direction of the wave propagation also subdivided, it subdivides into z sin theta and minus x cos theta. You can see z sin theta minus x cos theta, because you are in the reflected part, so that's why whenever there is angle, so it becomes theta r. It denotes that the reflected angle. Okay, minus iota omega t as it is. Now our electric field equation is done. Now we have to write the same for the magnetic field. We know that magnetic field is in the is into the page. Okay, for the case of into, we are using the negative direction, because electric field, if electric field and wave propagation in the x and z direction, so definitely your magnetic field is into the y direction. But either it is positive y or negative y, you can find by the right hand rule. Okay, if direction of magnetic field is into the page, then you have to use the negative direction. If out of the page, then you have to use positive direction. So in this scenario, this is into the page, that's why you are using minus y direction. And the magnetic field amplitude can be written as e naught, because you know that magnetic field is equals to h by z, where z is the amplitude, where z is basically the impedance, and e is basically the electric field. So H naught I can be written as E naught I divided by Z1. Why Z1? Because you are in the first region. Whenever you are in the second region, then you have to use the Z2, because the impedance of the second region. Because the impedance in the first region is Z1, so that's why it becomes Z1. And because the in the case of parallel polarization, only the electric field and the wave propagation splits, direction splits, but the direction of the magnetic field not splits. So that's why you can see only minus y, not cos theta or sine subdivision. So magnetic field is not subdivided into the more components. Only the wave propagation and the electric field direction is subdivided in the case of parallel polarization. Keep this important concept in your mind. Okay, so that's why this is minus y direction and amplitude is same. and the exponential is again same, because e power iota k1, because you are again in the first medium. But the wave propagation has to be subdivided into other components, because so we already know that in incident this is divided into z sine theta plus x cos theta. You can see z sine theta plus x cos theta, okay, minus your tau omega t as it is. Now move towards the reflected part of the wave propagation. Okay, to find the magnetic field again, by finding right hand rule, you are getting the minus phi direction for the case of magnetic field, and magnetic field is not subdivided in the case of parallel polarization, and you can see only left with minus y. And now you are in the reflected part, so the amplitude now becomes e naught r divided by z1, because now you are again in the first region. That's why z1 here. Again e power iota k1 as it is, and the subdivision of the wave propagation k is subdivided. Here you can see z sine theta minus x cos theta. You can see z sine theta minus x cos theta minus iota omega t as it is. So this is how you can write the electric field and magnetic field equations in region 1. Now move on towards the region 2. So in region 2 there is only reflect transmitted part, so things are now quite easy. Okay, so for the case of electric field, so the amplitude now becomes e naught t. In incident it becomes e naught I, in reflected it becomes e naught r. So definitely in transmitted part it becomes e naught t. An electric field component must have to be subdivided into other components, so you can construct like that: minus x sine theta and z cos theta. So minus x sine theta t plus z cos theta t, which is the subdivision of the electric field components, and e power iota k2. Now it becomes k2. Why k2? Because now you are in the second medium. Okay, and the wave propagation is now again subdivided, so you can see x cos theta and z sine theta, x cos theta and z sine theta t minus iota omega t as it is. Now you have to write the same thing for the case of magnetic field. As you know that magnetic field is not subdivided in the case of parallel polarization. Okay, so that's why there is by using right hand rule you can find the direction of the magnetic field. This is out of the page, and for this is into the page, sorry. Okay, so for the case of into, you are with negative and it is in the y direction magnetic field, so it becomes minus y, and the amplitude of the magnetic field now becomes e naught t divided by z2. Why z2? Now you are in the second medium. Okay, now exponential e power iota k2, and the wave propagation is again divided. You can see that wave propagation in x cos theta and z sin theta, x cos theta plus z sin theta minus iota omega t as it is. So now this is how you can write the field equations. Our next step is to apply the boundary condition. So the main important thing is that boundary condition is always apply with an axis with the normal line, as the normal line is in the x direction, so you have to apply the boundary condition at x equals to 0. Now let's just apply the boundary condition at x equals to 0. What you have to do, you have to put, whenever there is x you have to put 0. After putting 0 you are getting the results. So let's first write those results after putting the boundary condition at x equals to 0 in these field equations in region 1 and region 2. Now you can see by applying the boundary condition at x equals to 0 in these equations. Okay, so now first apply the x equals to 0 in the first region. Okay, in the electric field, what you have to do, you have to equal region 1 equals to region 2. In region 1 there is the sum of incident plus reflected, and when you equals to this, so incident plus reflected equals to transmitted. So by applying x equals to 0, so x equals to 0 you will only get with the cos theta component. Here when x 0 you will only get with z cos theta I, and whenever here x equals to 0, here also e power iota k1 z sin theta I, and e power minus iota omega t is common from region 1, and you can see e power minus iota omega t here and e power minus iota omega t here, also in region 2 e power minus iota omega. So take common from e power minus iota omega t from region 1 and cancel with the e power minus iota omega t in region 2. Okay, so you can see that e naught I, which is the amplitude, and this becomes 0, you will only left with z cos theta I. So you can see here is z and here is also z. Okay, and here is also, you can see z direction with z direction, because x is 0, you will only left with it. So take z common from these to this and cancels with this, so you will only left with e naught I cos theta I. So you can see e naught I cos theta I, and exponential power e power iota k1. You can see e power iota k1, and this x term goes 0, and you will only left with z sine theta I. So you can see z sine theta I. Similarly, you can see in this, here the x component becomes 0, so you will only left with e naught r. It minus becomes outside, so it becomes minus e naught r. Z cancels, cos theta r, so you can see cos theta r. And again exponential iota k1, so you can see iota k1, and the x terms go 0, you will only left with z sine theta r. You can see z sine theta r equals to the second region, which is the transmitted part. In transmitted part, this is e naught t, so it is e naught t, and this x term becomes 0, you will only left with cos theta, because z also 0, so cos theta t, you can see cos theta t e power iota k2 z sine theta t, z sine theta t, because this x cos theta t is 0, because x is 0, and e power iota omega t we are taking common, so you will only left with this. So this is our final equation for the case of when we apply the boundary condition on electric field, because you know that the tangential components of electric fields are equals. Okay, but here why you have to apply the Snell's law. So what is Snell's law? In Snell's law, the incident equals to reflected, means theta I equals to theta r, so that k1 sine theta becomes equals to k2 sine theta. So theta I and theta r becomes theta 1, and theta t becomes theta 2. Okay, and while whenever your k1 sine theta becomes equals to k2 sine theta in Snell's law, and so exponential this equals to this and equals to this, so exponential term take common from this, you have to cancel that exponential term with this, so you will only left with e naught I cos theta I minus e naught r cos theta r equals to e naught t cos theta t. So this is your final equation for the case of electric field. Okay, now you can apply the same boundary conditions on the magnetic field. So magnetic field, when you are doing x equals to 0, you will only left with minus y e naught, minus y is here, minus y is here, and minus y is here. You can take common minus y from here, easily cancels with this, so you will only left with e naught I by z1 plus plus e naught r divided by z1. You can see e naught I divided by z1 plus e naught r divided by z1 equals to e naught t divided by z2 equals to e naught t divided by z2. While these equations, how they cancels x terms, so you know that already cancels when, because x is 0, but e power iota k1 z sin theta, e power iota k1 z sin theta, e power iota k2 z sin theta can be cancels by the applying Snell's law. Okay, so by applying Snell's law, you can only left with this equation, e naught I divided by z1 plus e naught r divided by z1 equals to e naught t divided by z2. So what, take the LCM and move z1 to the other side, so it becomes e naught I plus e naught r equals to z1 by z2 e naught t. So this is your second equations. Now our task is to find the reflection coefficient and the transmission coefficient. To find that, so first of all, what you have to do, you have to find e naught t from equation number 2, finding e naught t from equation 2, and you have to put that value of e naught t in equation 1. So finding equation e naught t from equation 1, z2 multiplies to the other side, so it on other side becomes z2 by z1, so e naught t becomes z2 by z1, and this same, now you have to put this value of e naught t here in equation 1. So this is as it is, e naught I cos theta I minus e naught r cos theta r, e naught I cos theta I minus e naught r cos theta I. 1 is because theta 1 equals to theta r, so in region 1 theta I and theta r becomes theta 1 1, while theta t becomes theta 2, because you are theta t in the second region. Keep this in mind. So theta I becomes theta 1, theta r also becomes theta 1, and theta t becomes theta 2. Keep this, remember, in your mind. Okay, cos of theta 2 as it is, cos of theta t means it becomes cos of theta 2, and e naught t, which you already find here, so putting the value of e naught t, which is z2 by z1 e naught I plus e naught r. Now multiply cos of theta 2 Z2 by Z1 with E naught I and also with E naught R. So there are four terms. 1, 2, 3, 4. Now move, what you have to do, you have to move the incident terms on one side and the reflected terms on the other side. So here is the incident term, and here is you can see the incident term. When move is, it becomes minus sign, and here is the reflected term. Move this to the other side, it is becomes positive other side. So E naught R here, E naught R here, E naught I here, E naught I here. So what you have to do, you have to take common. E naught I is common. Okay, whenever you are taking E naught I is common, and also take Z1 common. So taking LCM, you will left with E naught I divided by Z1, this left. And whenever you are taking common E naught R divided by Z1 common here, you will be left with this. So Z1 cancels with Z1 because we have to find the reflection coefficient. We know that the reflection coefficient is basically the ratio of E naught R divided by E naught I. So E naught R is here. Move this E naught I here and move this to the other side. So final relation of the reflection coefficient E naught R divided by E naught I is equals to Z cos theta 1 minus Z2 cos theta 2 divided by Z1 cos theta 1 plus Z2 cos theta 2. So this is how you can find the reflection coefficient in parallel polarization. Now move on towards the finding of the transmission coefficient. Now to find the transmission coefficient, what you have to do, you have to divide your equation 2 by E naught I. So this is your equation 2, you have to divide it by E naught I. So when you divide E naught I by E naught I, it becomes 1. So you can see 1, and E naught R divided by E naught I, it becomes, and Z1 plus Z2 as it is. And when you divide by E naught I, so it becomes E naught T divided by E naught I. And now E naught R divided by E naught I, we already find here. You have to put the value of E naught R divided by E naught I from here to here. So this after putting the values. So now what you have to do, you have to take the LCM. So you are taking LCM. So Z1 cos theta 1 plus Z2 cos theta 2, which is the LCM. This multiplies by 1. So this plus this as it is. So Z2 cos theta 2 minus cancels with plus Z2 cos theta 2. So you will only left with Z cos theta 1 plus Z cos theta 1. So it becomes 2Z1 cos theta 1, and this Z1 by Z2, when it goes to the other side, it becomes Z2 by Z1. So Z1 cancels with Z1, so it becomes 2Z2 cos theta 1 divided by Z1 cos theta 1 plus Z2 cos theta 2. So this is the this is the transmission coefficient. Okay, so that's all for the parallel polarization of electric and magnetic field, in which we successfully find the reflection as well as the transmission coefficient. Okay, there is also a small topic which is called as power, also known as the Poynting vector. We can define it by is the intensity. Okay, intensity of the electric field. So Poynting vector can be written as 1 by S, denoted by S, written as S equals to 1 by 2 real in the cross product of electric field and the magnetic field. Okay, so here E cross H, okay, star, and we know that H basically equals to E by Z. Okay, whereas Z is the impedance, so H star becomes E star divided by Z. So multiplication of E cross E star, it becomes mod of E square, okay, divided by Z, which is the impedance, and the direction of the Poynting vector, means the direction of the intensity. Okay, direction of this Poynting vector. So this is the final expression of the Poynting vector. S equals to 1 by 2 the mod square of electric field divided by Z, which is the impedance, and basically it shows the direction of the Poynting vector. Basically intensity is proportional to the amplitude square. So you can see this is the amplitude of electric field, so you can easily define the intensity is basically proportional to the amplitude square. Okay, so taking the amplitude squares of either, you are getting the intensity. Okay, we have amplitudes here, we already find the reflection coefficient as well as the transmission coefficient. By taking their squares, you can easily find the intensity, okay, of those amplitudes, and the unit of this intensity is watt per meter square. As you know that E naught R divided by E naught I is basically the reflection coefficient, but by taking the mod square of the reflection coefficient, you are getting the reflectance denoted by R, and by taking the mod square of the transmission coefficient E naught T divided by E naught I mod square, it becomes transmittance and denoted by T. Okay, so by taking the amplitude square, you are getting the intensity. So reflection coefficient becomes reflectance and transmission coefficient becomes transmittance after taking their mod squares, and the sum of reflectance plus transmission always equals to 1. So that's all for this lecture number 13 for uh, advanced electromagnetic field and waves. We'll also upload in next video about the perpendicular polarization in lecture 14. So till then, take care. Allah Hafiz.